Power converters in high-growth markets like renewables and AI are increasingly integrating SiC MOSFETs and GaN to benefit from the higher efficiency and power density they offer. But developers often struggle to implement isolated gate driver circuitry that meets the EMI and EMC limits. So can planar transformers help tackle this issue? Do any new challenges arise as a result? And how do they support the latest power topology trends to reduce geometries and increase power density? I'm Stuart Cording, the electronics reporter, and in this episode of Mauser Talks Tech, I'm talking to Cathal Sheehan, Application Director, Power Division at Bourns, Inc. So, hello, Cathal.
Hi, Stuart. How are you?
I'm good. I'm really pleased to have you here because I think this is a very interesting and exciting topic. It's very niche as part of the power conversion system, and yet it's really, really important. So to get started, I thought I'd first ask you to explain the different types of applications that you're covering with these planar transformers. Which application domains have really committed to swapping out their silicon MOSFETs for wideband alternatives like SiC MOSFETs?
Thanks, Stuart. Very good question. I guess over the past couple of years now, we are seeing the amount of demand for energy from the grid increase quite a lot, most notably for artificial intelligence infrastructure. And what's happening is the way to, because copper costs a lot of money, and if you're increasing the amount of power going through the copper, you have to come up with a way of reducing the amount of copper. So what we are seeing happening is first of all, the voltages are increasing. That helps reduce the amount of copper and deliver high amounts of power. And at the same time, we're seeing more everything head towards more DC, so HVDC. So let's say, move away from the traditional 50 hertz grid and towards a more high voltage DC supply. And one of the reasons for that, of course, is even 50 hertz, which is 50 times per second, introduces problems with the skin effect, which notably causes higher losses in copper conductors. And one way of avoiding that is switching to DC. So that means we're going to have higher voltages, working voltages. We see 800 volts more often now. We see solar inverters with solar cells producing outputs of over 1,000 volts, 1,500 volts. All of this means that the converters themselves, the actual switching devices, need to have higher working voltages. And so silicon carbide in particular is something which has, you can get modules now which are over 2,000 volts on the market. Gallium nitride is a little far behind in terms of voltages. I think, you can get 600 volt gallium nitride on the market, but silicon carbide seems to be the one that's preferred for high voltage applications in the areas I was talking about, which would be renewable energy and solar, things like that. Yeah.
Now, for those with sort of less experience with SiC MOSFETs, how does the gate driver then need to be modified when transitioning away from classical silicon MOSFETs for these applications?
So, quite simply, in layman's terms, the gate of the device has to be driven with a higher voltage than a MOSFET. So it would 15 volts to 24 volts to activate the device, and then it needs a negative voltage to bias it off. So you'll be looking at a kind of a circuit that would be able to provide, let's say, plus 15 volts, minus 5 volts. And in order to do that, you need a bit more power as well. When you're operating those high voltages, you need a bit more energy to turn on the gate and turn it off effectively. So you need a kind of an auxiliary bias supply which can provide isolated plus 15, minus 5 volts on the gate side of the driver. MOSFETs would only require 1 voltage to turn it on and 0 volts then to turn it off. So it's a more complicated schematic or setup required. Yeah.
Yeah. So we've got higher voltages to control the gate. We've got the switching frequencies are much higher, can be much higher than in silicon MOSFET designs. What are the challenges in that auxiliary gate driver circuitry that result from this change?
I think you need a kind of a power supply that can generate the output on the gate side, plus 15 minus 5 volts. So you need a kind of a first of all, I suppose what's important is because we're operating in an environment with a very high working voltage, the circuit itself needs to have a high level of isolation. So you need to be able to be sure that you have the high level of isolation so that there's no risk of any electric shocks, on the digital side happening. And when you're talking about working voltages of 1,000 volts or 1,500 volts, the isolation requirements get a lot more difficult. So that does introduce some kind of complexity. So you do need a transformer with very good isolation to provide those voltages. Whereas maybe in the past you didn't need to have a kind of a transformer isolated converter. Now you do. So the type of converter used then can be there's different ones out there. Flybacks are used, or push pulls are used, or resonant converters are used. Push pulls are limited in the sense that they have to have a very fixed input voltage when you're to obtain the highest efficiency. Resonant converters don't need that same level of fixed input. Flybacks, you can have a very wide input range coming into the flyback circuit. So there's different topologies, there's different chips out there that, but really what you want to do is, because you could have several driver circuits operating, you want something which is as cost effective as possible, and something which requires as let's say little amount of components as possible, and one that is requires less control. So what would be most favourable would be, let's say, a kind of a driver type circuit without a control loop, something that can be set up without having to worry about things like control and stability and things like that.
Yeah. And I imagine also in one of the challenges that arises with all those currents flowing is EMI problems.
Yes, indeed. EMI problems are something which can creep in, especially when you're operating with high voltage devices. As you can imagine, you're going to have the drain of the switching device going from a high voltage to a low voltage in a very short period of time, because they do operate at a high frequency. So this transition, this DV/DT, can induce common mode currents, which can get back into the ground plane and get back, causing problems with emissions. So everything there, so any of the parasitics associated with the gate and with the gate driver circuit have to be controlled and minimized, in particular capacitance. So any gate driver capacitance has to be eliminated. And indeed, if you're using a magnetic device, for example, the interwinding capacitance needs to be minimized as well to reduce any common mode currents.
So that's a great introduction to some of the complexities and challenges around that. I was looking on the Bourns website and I found a circuit for the auxiliary power gate driver design. Why don't you take us through the common approach for that circuitry so that we can understand in detail how it's implemented?
So it's our approach would be to try, first of all, as you said, minimize EMI emissions. Using a resonant controller, you can create a current in the primary side and on the secondary side, which is a pure sinusoid. So one harmonic and at a high frequency. So higher frequencies are also easier to attenuate and filter out. on the common modes in the common mode chokes. So a high frequency transformer driver, we work quite a lot with a very good driver. It's the UCC 25800. It's a transformer driver which requires just an external a capacitor, and then the inductance in the transformer itself to form a resonant tank. And this circuit can operate. It can operate at any frequency you want, depending on the capacitor and the inductance of the transformer. We have run it at up to a megahertz, and we're able to get up to a couple of watts of power out of a very, very small planar transformer. And then after that, then just using some voltage doublers on the secondary side, you're able to create the voltages you require for the gate. So for the gate driver chip. So the gate driver chip will need 15 volts and minus 5 volts on the isolated side, and that's where the power supply would generate it. And it's quite a very simple, compact circuit.
Now, in the past, I think one of the only choice would have been a wire wound transformer. That's sort of like the classic approach to the transformer part of this design. But Bourns has a range of planar transformers that can offer better performance for these high frequency, high power gate driver circuits. Can you just explain to us how a planar transformer differs from a more classical wire wound design?
So for a planar design is typically consisting of a spiral coil on a plane. And if it's a transformer, you would have a primary side with one spiral, and then a secondary side, another spiral directly located underneath that. The separation between them can be controlled to a very fine level. The assembly of the transformer would be quite straightforward. Once you let's say print the windings, the coils on the planar substrate, the assembly is quite quick. Whereas in a concentric transformer, you need a winding machine. You need to have a kind of a coil former. You need to wind the coils. You need to solder the coils to pins. You need to then put tape on it as well for isolation. A lot of those steps are eliminated using a planar device because the printing takes care of the coils. The terminations are also printed. So there's fewer steps in assembly, and at the end of the day, you end up with something which is quite thin, quite low profile, which is something which you wouldn't be able to do with a concentric wound transformer. You would have you would always have limitations in the height of the transformer if it's concentric. Whereas with a planar device, you can make it really, really ultra thin.
And just on the point there, you said the substrate. What sort of substrates are used for these planar transformers, and what are the key sort of improvements in the datasheet numbers that I'm going to see in a planar transformer versus a wire wound one?
The planar transformer substrate, well, FR4 would be a very common one. FR4 is used a lot for printed circuit boards. It's quite commonly known. So you can use you can lay out your spiral on using an FR4 substrate. You can pick the thickness of the copper to be whatever you need for, depending on the current density. So that could be 35 microns. That's or it could be a 1 micron of copper. 70 microns of copper. So it can be quarter ounce, half ounce copper, whichever, depending on the current density. And FR4 has a very strong advantage as well now in this area of high voltages. The electric strength of FR4 is very, very strong. It's in fact it's up to 30 kilovolts per millimeter. So that really makes it an excellent isolator for high voltage applications.
And what are the parasitics like in those planar transformers for this, and how does that impact these isolated gate driver circuits?
The parasitics can be I suppose when you have a concentric wound transformer, you do have a very wide. Even in production, you're going to have a certain, let's say, tolerance in some values like parasitics, because the parasitics depend on the gap between the primary and the secondary, and you're going to have a kind of a wound structure on top of tape. There could be air gaps inside there, things like that. So controlling the tolerance there is one thing, but when you have let's say a planar design, particularly a very small device like a very small planar transformer, the coplanarity is very good, and then once you have a production line set up, the tolerances in the gaps between the coils is infinitely better than a concentric transformer. And of course, as we know, the interwinding capacitance between two coils depends very much on the dielectric you're using and the gap, the distance between them. So by controlling that distance, you are also controlling the capacitance. So you can make the capacitance much smaller by just increasing the gap, and then the spread over in a production environment is much thinner compared to a concentric transformer. So overall, it offers good advantages for controlling things like capacitance, which have a big impact on EMI in a high voltage silicon carbide module.
Well, that's very helpful to understand and get a feeling for the improvements that are on offer. Imagine then for a minute that I'm a power converter designer. I'm exploring SiC MOSFETs for my next application. What planar transformers are on offer from Bourns that would be suited for this auxiliary power isolated gate driver circuit?
Yes, so Bourns are have released now a miniature series of planar transformers, ideally suited for the UCC 2580. So this is it's called the SM9127X series. It's a series of miniature planar transformers with a profile height of only 6 millimeters. They are available in tape and reel. They can be placed on a PCB with a cutout in the middle of it for better heat transfer, and they can operate at anything up to 4 watts of power at 1 megahertz. So they could even be used to deliver power to more than one gate driver IC if necessary. And they have been fully qualified for automotive applications. So they've been fully tested for automotive. They also have very high isolation. As I said, they're using FR4 material, so they can pass a dielectric test of 6 kilovolts. And they also have been approved for partial discharge testing. So the charge would be less than 10 picocoulombs with an applied voltage of 1,500 volts RMS. So these would be suitable for inverters, DC-DC converters, where the operating voltages are anything up to 1,000 volts.
Well, that sounds like a lot of SiC-based wide band applications are covered. Now, we've heard a lot about the benefits of planar transformers over wire-wound alternatives. For those choosing to use them for the first time, are there any sort of gotchas that people should be aware of before designing them in?
I suppose the main thing to be careful of is just the frequency. So we would recommend that you operate them at as high frequency as possible to get the best efficiency out of them. There might be reasons for operating at lower frequency, but if you do that, the efficiency will decrease. So we recommend operating at the highest frequency possible at a megahertz.
Super. Well, that's a great overview of the planar transformer technology from Bourns and how to apply it into power converters. And as you said, there's so many different applications out there which are demanding this higher efficiency in power conversion. We've got data centers for AI and just classic data centers, solar inverters, and so on and so forth. So it's great to see that there's some innovation going on in that domain as well to support that shift to wide bandgap switches. As we always do in our Tech Talks interviews, we've also reached out to our community with a few questions. And one of the things I wanted to ask you first was, or share with you at least, was the results of a poll that we did. So we did a quick survey to ask people on social media if they're already using planar transformers or if they're still using wire-wound transformers. And 57% said that they're already using planar transformers versus 43% who said they're still using wire-wound. Does it surprise you that so many people have already transitioned across?
No, I think I can see a trend towards planar for many reasons. Now, you can't use, I would say, planar. Using planar for every type of application is not convenient because, for example, if you have a circuit where you have quite a large input voltage, the volt seconds created would be quite high, and you would need a very large number of turns to keep the flux under control in the core, and that often it makes the design of the windings quite complicated, especially if you don't have a lot of space available. So in those situations, a concentric is convenient. However, if you are operating at a reasonably low voltage and a high enough frequency, then yes, a planar transformer makes good sense. And then, as I said earlier, the actual benefits of FR4 offer very good isolation as well. So even if you're operating at a low voltage, but you're in a high voltage working environment, you can use them there as well. So there's definitely doesn't surprise me, I have to say.
Well, that's good to hear, to see that our community is moving with the times and trying out new technologies as they become available. One of the other questions that came up, and I think it'd be worth asking you as well, is how will a planar transformer behave thermally on my PCB? Do you have any guidelines that you can offer on how to deal with maybe the heat dissipation on these devices?
Okay, very good question. I suppose there's a couple of things to be aware of. The first thing is what turns ratio are you going to use? So if you use the SM9127X and you're going to have a step up turns ratio, which is to be expected if you're doing a kind of an auxiliary supply for a gate driver IC, where you might have 12 volts in and you want 24 volts out. So you would need a 1:2. And in that situation, the power rating would have to go down because you're going to have a lot more current, let's say, or going through the primary side to supply the energy on the secondary side. So in that situation, the best thing to do is to derate the power, keep the power dissipation underneath. I mentioned 4 watts earlier, perfect conditions, but I would maybe thermally speaking, best is to keep it under 1.5 watts maximum power dissipation. The other thing I would say as well is, it's what you could look at is putting a cutout in the PCB and have the core fit through the cutout and maybe have it sit on some sort of thermal gap filler, something like that. So that can help remove the heat from the device and put it outside. And it very much depends again on what kind of convection is in the system. Maybe there's some airflow provided anyway. If it's a large enough system, that would certainly help. But we have tested these devices up to up to 80 degrees. We don't see any significant increase beyond 20 to 30 degrees at 2 watts. So I think as they are, without any special air convection, they should be able to handle the power that we specified on the datasheet.
Yeah. Well, that's great to hear. That brings me to another point, because I think one of the things as engineers that we are interested in, we spend a lot of time with one component, learning all about it, and we understand at what point they can fail, at one point we can't rely upon them anymore. For those who haven't used planar transformers before, what sort of failure modes you'd expect from them, and does that differ from the failure modes you'd expect from a wire wound transformer?
I think by their nature, planar transformers are quite low profile, and they have, let's say, a wider surface area for the same size compared to concentric. So the thing to watch out for there is mechanical stress. If, for example, you're putting it on some sort of thermal gap filler or something like that, you just got to be careful that the thermal stress doesn't cause any damage to the core, maybe some cracking of the core or something like that. So that's something which you wouldn't really see in a concentric wound transformer, where the core is kind of slightly lifted off the board by the bobbin itself, whereas a planar transformer, the core is typically going to be touching something like a PCB or something like that, and they're quite thin. So just the mechanical design of the system needs to take that into consideration to avoid any mechanical stress on the component. Yeah.
Okay. Super. That will be helpful as people transition across them, for those who've not used them before. We're coming towards the end of our time, but I still wanted to try and get one more question in before we lose our expert on this topic. For those of our community who want to get started with a planar transformer and see it running in a system that's actually been designed by experts and can be used as a reference point, do you have any guidance on development boards or reference designs they could turn to?
Well, we actually are, as part of the release of this transformer, we have developed a half-bridge reference design board. So it consists of 2 gate driver ICs, 2 auxiliary power ICs with the planar transformer, the SM9127. And we also have populated it with 2 silicon carbide MOSFETs. And this can be used as a half bridge for a DC-DC converter, for example. The actual inputs to this device are power, of course, and as well as that, then that's basically it, because the gate driver ICs, everything, they're all powered independently. So, I mean, it's quite a useful board, and we will be publishing that online on our website as well for if people want to get a copy of it.
Super. Well, it's been a very informative discussion, and I really appreciate you taking us through the sort of like the benefits of planar transformers and how they're supporting that move to wide bandgap technology in power converters and inverters. Thanks, Cathal.
Thank you very much for having me, Stuart. Appreciate it. Thank you.
So that wraps it up for this edition of Mauser Talks Tech. What have we learned? The power converter landscape is evolving thanks to new switching technologies such as SiC and GaN and the applications they enable. But this is causing new design issues thanks to higher voltages and currents and higher switching frequencies, resulting in more complex EMI challenges. But there are solutions. In the gate driver design, planar transformers offer benefits over wire-wound alternatives thanks to their small size and lower capacitive coupling, which limits common mode currents. This, combined with the higher electrical isolation provided by the FR4 material used in their construction, makes them ideal for wide bandgap power converter designs. My thanks go to Cathal Sheehan from Bourns for sharing his technical insights today. And if you'd like to learn more about the range of planar transformers discussed here, follow the links in the description below. Thanks for watching, and see you next time.